what was given, I think for the most case. I changed some values, but nothing of that significant. So let me go through this. So on the first problem, it's basically something that has a shunt. Short circuit shunt, and then you have a load. And Z naught on this one is 50 ohms. Here ZL is equal to 40 plus J10. And we want this length, and I believe I call this D, and this length, I think L, but I'm not absolutely certain. We wanted them in meters. And the frequency was 750 megahertz, and the velocity on the line was equal to C, so the wavelength was equal to C over F, and that's 0.4 meters. I'm just putting down this, because this is very direct calculations, nothing. So the starting point is always finding small ZL. That would be your 0.1, and that's equal to simply ZL over Z naught. And that equals 0.8 plus J 0.2. Is everybody okay with that? All right. Now on the Smith chart, and I'm going to just scratch one up here. That's the one circle. That point, 0.8 plus J.2 is about here. So this would be ZL and 0.1. So I expected to see something like this. And a straight line through here. The next point, 2, is YL here. And that's the point you move from. All right? Because it's, remember, these are in parallel or shunts, so we're working in the Y admittance domain. Everybody understand that, class? Remember this problem, by the way? Anybody? I think it's the exact problem I did for homework. Literally. I don't even think I changed the values, but I'm not absolutely certain on that one. You all see what I'm doing here? All right. Now, we're at YL here. And when we look at this, I think it's 0.32 something wavelengths towards generator. Do you all see that point? What, Josh, what did you have for the exact value? Because yours was right,
Yeah, 0.32.
And you can just take a straight line there and see. Remember, I'm working on the outer circle, wavelengths towards generator. Now we have to move from here all the way to the one circle. This would be 0.3 right here. And this will have a value of 1 plus J 0.3 approximately. Remember, that's Y. Does everybody see that point, class? Now when you have that, you've got to throw another line straight through here. And you're going to come towards, I think it's 0. Is it 1.4 wavelengths towards generator?
Yeah,
1.4 wavelengths towards generator. Remember, those are fractions of wavelengths. So now, the first thing I'm going to do is calculate D. And D would be the movement from here to here. And this would be the distance D. So when I calculate that, first in wavelengths, D would be equal to 0.14, I'll put lambda in there, minus 0.32 lambda. I know that's going to be negative, so I add 0.5 lambda to that. And I think D becomes 0.32 lambda. Tell me if that's right. Is that what you got? Okay, with me on this one? I'm just subtracting this point. Take this as the lead point, because that's where I went to. Subtract this from it. I know it's negative, so I add half a wavelength. Everybody got that, class? And that comes out to, in meters, help me out here, John. Which one is it? What is it?
0.128.
0.3, what?
0.128.
0.128 meters, and that would be the first part. Now, I have J.3 here, which is positive, right? So again, with this stub tuning, since this is a shorted stub, the impedance of the load is 0. The admittance would be infinite, correct, class? Right? And we want to get a value of minus J.3 to attach we wanna make sure that right here, this stub has a value of minus J.3 in the admittance domain, correct, class? So the impedance of the stub was 0, would start here, therefore the admittance of the stub would be infinite, would be right here. And this is the point of infinity, and it's also at 0.25 lambda wavelengths towards generator. Please make sure you see that. People made a lot of mistakes right here. Understand, class? Now I have to move. Remember, this is going to be the stub now. And now I'm going to move till I hit the point 0.3 J. It's minus J 0.3. Do you all see this, class? Now look on the outer, make sure you see this. This is going to be indicated by little dash marks on your Smith chart. I think from now on, I'm going to have to bring Smith charts because I had a variety of different Smith charts. Some had a more detail and were better, some were not so good. And it was very hard, I think, for people to read some of this stuff on your Smith charts that you brought. Remember that big one I gave you out and you could copy? That's the best one. All right, now this distance from here to here, actually, what am I doing? It's way over here. This is over here. It's minus J 0.3. And the stub, therefore, would go from here to here. Can you all see that? I'm sorry to put it there. Understand? You all see that point? Make sure you can see this point, 0.3. Won't have the not minus on there, but anything in the southern hemisphere is negative with J's. Remember that. Got it? Because you're going to see this stuff again on the final. I just want to make sure we're clear about it. Now, I need the distance, so it starts at 0.25 lambda, and this point, I don't remember it off the top of my... 0.45, is that what you have? Mm-hmm. This is 0.45 wavelengths towards generator. So that means for L, it would be equal to 0.45 lambda minus 0.25 lambda, or 0.2 lambda, and L comes out to, what was it exactly?
0.08 meters.
Yeah, about 0.08 meters. And those are the two values, and that's how you do it. Please make sure if you made mistakes, you clarify, you really clear up what the problem was, because you're going to see Smith charts again and again and again. You're going to see them in EMAG 2, you'll see them in other classes in microwave, you may see them in a couple other ones, EMC, I'm not sure if wireless uses it, but amplifier design, high frequency amplifier design, a lot of different courses rely on Smith charts for design applications, and you have to understand how to use it. So please make sure. Any questions at all? All right, I'm going to say one other thing on this problem. I probably at some point will ask you also, if I put a generator here, I'll ask something about the standing wave ratio, things like that without the stub, and the amount of power coupled to the load without the stub, then the amount of power coupled to the load with the stub. You follow me on that, everybody? So be aware I'm going to keep on using this type of format for problems, this thing. Okay. Next problem. This is the one where just you have to be familiar with the electric field from different charge distributions. So, problem 2, and they have a charge. Can you give me these things? Q equals 6 microcoulombs at, is it 0, 0, 1? Is that it? Or?
Yeah.
All right, and then we have a line charge, rho L, that's equal to, give me the value.
180 nanocoulombs. And it lies
Per
along
meter. And it's at what point?
It lies along the x-axis.
X-axis. And then finally we have rho S. I think it was rho L by misprint, but the units are Rho S equals what?
25 nanocoulombs.
25 nanocoulombs per meter squared at,
Z equals -1.
all right, so what I'm gonna do is get the electric field from each one of those, then add them together. All right. So for the first one here, oh, I want the electric field at the point, is it 251 or
152.
152? All right, so that's where I want the electric field. So first I kind of sketched this to help me. That's Y, and this is Z. And the first one is 6 microcoulombs at 001, so that's 001 is right here. Here's where my charge is. And then I want the field at 152. That would be 152. So this is the E at 152 that I want. And for this one, now I need to get R vector. I need to get a vector R here. That's going to be from the point where the charge exists to the point of observation. With me, class? So what is R? Well, you always take the coordinates of the point of observation minus the source coordinates. It would be 1 minus 0, or it would be 1AX. Then it would be 5 minus 0, or plus 5AY. Then it would be 2 minus 1, or plus 1AX. That would be R vector for this one, right? Now I need R magnitude, and that's just going to be the square root of 1 plus 25 plus 1, right? Or square root of 27 is R magnitude. And then AR is just R vector over R magnitude. I'm going through it systematically here to make sure there's no problem. A lot of people forgot the vector. They just put AZ there or something, and I don't understand where, they didn't understand how to do what I'm doing. Understand this so far, class? So if you take a look at this, this is really this vector divided by square root of 27. Now, when we get the E field, in general, it's Q, which is 6 microcoulombs, over 4 pi epsilon naught, and you can use 1 over 36 pi times 10 to the minus 9th if you'd like. And then it's over R squared, which is going to be square root of 27 squared, or just 27, right? And then it's going to be times AR, which is really this over that, or it makes 27 to the 3/2 power, and then it's times AX plus 5AY plus 1AZ. So that's the electric field from there. And then when you do the math on this one, that cancels this. And then I have 4 goes into 36 as 1/9 right here. So that becomes a 9, and 9 comes up here, right? So that gets rid of all that. And then I have micro, I'm gonna leave it like this for right now, but that would be the electric field, right, class? And you can break that out. I have the actual value for that, but is everybody following me on this one? Did you have this actual value? I peeked my notes.
384.9.
384.9 AX, go ahead.
And then, actually, I didn't write down all that.
Do you have this?
Not the
All right, don't worry about this part, because this is just the mathematics of doing that. All right, I looked at the final answer, but I made sure if you had that part right, you got credit. I had to see it though. I mean, I had to literally see something that indicates you knew how to do that part. Then the second thing is from rho L. So this is gonna be from line charge, rho L, and that's equal to 180 nanocoulombs, 180 nanocoulombs per meter. And it was located on the x-axis, so that's this axis. So I want, now let's call this, I'm gonna call this rho vector. You can call it R if you want, but it's the perpendicular, it's a vector drawn perpendicular to the charge, the line charge to the point of observation. Right, from the charge to the point of observation. So here, rho vector is just gonna be what? That coordinate here X you throw out, it's just going to be a function of y and z. Do you follow me on this, class? X is infinite. So here, it's really going to be 5ax plus 2az, right? Because you take the coordinates, the point of observation, 5 minus 0, ay, 2 minus 0, az. Correct, class? Now I have that, then I need rho magnitude, which is simply square root of 5 squared plus 2 squared, or 25 plus 4, or square root of 29. And then I can take a rho here, and that's equal to simply rho vector over square root of 29. Right? And now I can say that the E field from the line charge, E field from rho L is equal to rho line charge over 2 pi epsilon naught, and then it's going to be a rho. So here, E rho L is equal to rho L, which is less 180 times 10 to the minus 9 over 2 pi, and then it's going to be 1 over 36 pi times 10 to the minus 9. Then it's divided, there's a rho here, by the way, divided by the magnitude of rho, which is square root of 29. Then it's times a rho, and that has the square root of 29 in it again, so it just makes 29 down here, and I have 5ax plus 2az. I have the values for these if you want to take a look at it. First, you see the 10 to the minus 8th cancel. Then you can see the pi's cancel. And then I have 2 over 36, or really 1 over 18. So I can take 18 up here, and I can do the math from there. But that's basically what I'm talking about doing. So you're going to get a number for this. I have this written out. I don't know if it's worthwhile getting the actual numbers for these. We can, but I mean, literally, if you look at this, this is just a constant times these values. I can get that for you, though, if you want. I have it written over there. I prefer not to. Well, actually, I think it's on my computer. I don't think it's on the paper I've got. But that's what it's going to be from the line charge. Follow me, class? Finally, for the sheet of charge, this is going to be for rho s equals 25 nanocoulombs per meter squared. Rho s is at minus z equals minus 1. So z equals minus 1 is here. It means it's a sheet of charge in this plane. Giant sheet of charge. And we know the electric field will always be perpendicular to the sheet of charge pointing away from it, correct, class? So I know above it, it's going to be pointing strictly in the AZ direction, and our point of observation is above it. Does everybody agree with this? So that means the electric field here from rho s will just simply be rho s over 2 epsilon naught, and then it would be in the A normal direction. Here, A normal is AZ. Rho s is 25 times 10 to the minus 9 over 2, 1 over 36 pi times 10 to the minus 9 in the AZ direction. So that goes, and then I have really 2 into 36, 18. So if you look at this, what is that? 25 over 25 times 18 pi. I believe that's right, isn't it? 25, 18 pi AZ. And that's volts per meter. All these, the default units rate are volts per meter. I don't know what that value is off the top of my head. Do you have that, anybody? Just do 25 times 18 times pi.
1,413.7.
1,000, say it again?
413.7.
AZ, and that's volts per meter. Thank you. So finally, the total electric field here will just be E of the point charge plus E of the line charge, rho L plus E of rho S. That one I'm going to put down. And that value, when all is said and done, should be equal to 384.3 AX plus 2483 AY plus 2020 AZ. And that's volts per meter. And that is the answer, but it's really just adding them up vectorially. So you're gonna have to add up all the components in the X, Y, and Z. Correct, class? This is just a test to make sure you first understood what the electric field was from each of those charge distributions. Then you knew how to go ahead and add them together and not make a mistake. And that's basically was it. Any questions about that problem? Now, as I recall, there were quite a few people that had trouble with this one, and I think the trouble mainly lied in this, getting these vector directions. So please make sure you know how to do that from henceforth, because you're going to use vectors a lot, everywhere, in EMAG, and you're going to use them in all your other courses. So please be careful about that. All right. Was this a homework problem, by the way? It wasn't. Wasn't it on chapter 3? I thought that was.
There was one like this, but the point you were looking for was at the origin.
The electric field
And-
was at the origin?
Yeah,
Okay.
and each of the charges only acted in one direction.
Okay. Anyway, that's the basic problem, and it wasn't meant to be tricky. All right, next, it's a spherical charge distribution, and we have rho v equals 1 over r squared nanocoulombs per meter cubed for r less than a, or capital R less than a, then rho v equals 0 for r greater than a. Right? And I wanted the D field everywhere. And I usually ask for a sketch. I didn't in this one, but remember this from now on, I'll probably ask for a sketch. And I give about 2 to 3 points for the sketch, so you have to be able to draw it. So for starters, this is definitely a Gauss's law problem. And that's the integral of d dot ds is equal to the integral of rho v dv. And that's what it is. When you take a look at this, if it's a spherical charge distribution, or spherically symmetric, right? Come out here and you basically have a ball, and this ball has a radius of a, and everywhere in here it's rho v. So if I come out a distance r away, and I put down a Gaussian surface, I know if I'm at r less than a, greater than or equal to 0, less than or equal to a, I know that the integral of d dot ds here, the integral of d dot ds becomes 4 pi r squared dr. I can write the integral for you if you want me to and do it in terms of the differential surface or differential volume, but I think we all know it's the surface area of a sphere, 4 pi r squared times dr. Is everybody clear on that, class? Now we can do the surface is r squared, then it's going to be sine theta d theta d phi, and then do the integral, but it'll end up as 4 pi r squared. All right? Now on the other side, now it's the integral of rho v dv. Well, that becomes the integral, triple integral. Rho v is 1 over r squared, it's times 10 to the minus 9, because it's nana, right there, nanocoulombs. Then it's times the differential element of volume, which is going to be r squared. Then it's going to be times sine theta d phi dr. And right off the bat, you can see the r squareds cancel, which is the intent. Make it as simple as possible if you know that, right? Now after that, sine and theta here, because d theta is the first one, goes from 0 to pi. Phi goes from 0 to 2 pi. And r goes from 0 to r. And technically, I should prime that, right? But the r squareds cancel. Do you all agree with me, class? All right, so what you're going to end up with is the sine integral becomes minus cosine, evaluated from 0 to pi is a 2 value, right? And then d phi from 0 to 2 pi is 2 pi, so that's 4 pi. And then the integral of dr prime from 0 to r is just r. So here we're gonna get 4 pi r times 10 to the minus 9. Y'all agree with me, class? And therefore, when we find dr here, it's gonna be 1 over 4 pi r squared here, and then it's gonna be times 4 pi r 10 to the minus 9th, or it's just really 10 to the minus 9th over r is dr. And that is for r less than or equal to a, greater than or equal to 0. That's the first part. Agreed? Any questions so far? Now, after that, when we go to r greater than a, then the integral of d dot ds over the surface is still equal to 4 pi r squared dr. I hope, does everybody agree with that? But now it's the total charge enclosed. So the total charge enclosed is going to be the same darn integral, 10 to the minus 9th over r squared times r squared sine theta d theta d phi dr, and 0 to pi, right? 0 to 2 pi, but now this one goes 0 to a. That's the only difference, right? Because now all the charge is limited to the radius of a. Understand, everyone, class? People made mistakes. I saw d of r equals 0 out there. Remember, it's all the charge that's inside that sphere of the radius greater than a. And that's all the charge that's in that ball right there. Follow me, class, on this one? Now, here, that's going to be d of r is equal to 1 over 4 pi r squared. And then it's going to be simply, well, the r squareds cancel there. I have 10 to the minus 9. And then I have 4 pi a, don't I? Agree? And here, you can see the 4 pi's cancel. Equals to 4 pi cancels, and so I have 10 to the minus 9th a over r squared is equal to dr, and that's for r greater than a. Are there any questions at all? Remember this one thing, once you're outside where the charge, where the charge density is actually contained within, all the charge is contained within the radius a, right? It's less than or equal to a. Once you're outside there, you just lump all the charge as if it's at the origin. And that's what we're doing here. We're literally lumping it all at the origin. And it's falling as 1 over r squared. Now, if you were to graph this, and this is one thing I will be asking for next time, it's likely I will, and this is 0 and this is a. Well, if you take a look at this, the first part right here, d of r right here looks like it's coming in at a value of infinity at 0, right? And in fact it is. So asymptotically it's coming in at infinity. And then here, when it hits a, it's just 10 to the minus 9th over a, and it'll match that one, and then it starts falling off as r squared. This is a 1 over r. And this will be 1 over r squared, which is a little more appreciable fall. Something like that. And if you want the value right here, that would be 10 to the minus 9th, a, 10 to the minus 9th over a, pardon, right there. And that would be right at a, and that would be the value of d. Follow me? All right. Wasn't meant to be hard. Any questions at all? That's 3. Next we have, we want the resistance between the ends of a coax. So really we got this. Got something with sigma 1, something with sigma 2. This is radius A, I believe. And this is radius B. And it's got a length L. And what I'm looking for is R. And this surface was capital A, and this surface was capital B. So I'm looking for R between A and B. There's a couple different ways to do this. I'm going to just go through the easiest way. Y'all agree we can think of these as two resistors that are in parallel? The first one being the core region, right? From 0 to A, that's one resistance. Y'all agree with that? Because all the current flow is this way. All the current flow is this way. If you think about it, we put a voltage there. So we have a core resistance here with sigma 1. Then we have another resistor that's like a larger core with the inner part taken out, right? A cored out. So do y'all agree that that could be looked at as two resistors in parallel? How many see this? That's the way I was hoping you saw that. So resistance in general for something of constant cross-section is always L over the value of sigma divided by the cross-sectional area that the current's going through. Remember, the cross-section cannot vary for this. Do you remember this formula, class? Do you remember me going through it? You know? How many do, honestly? Because I went through this, I did it on purpose to show you how you could see things in parallel. Okay. Remember when I was saying if they're in parallel, just do them in parallel, the capacitors in this one?
Yeah.
It's easier to do it this way. Now, if I look at R for sigma 1, well, L is the same in both. This is sigma 1, and the area is simply just pi a squared. Do you all agree with that?
Are you sure?
Are with me? Now, what about R for the region in sigma 2? Well, that's still L. This would be sigma 2, but what's the area? Now it's pi, and it's going to be b squared minus a squared, right? It would be the area, the larger area, minus the smaller area. Do you all agree with that? And again, I'm just showing you one method. There's several. Now I can say that R total would be, since they're in parallel, it's 1 over R sigma 1 plus 1 over R sigma 2. Or it would be equal to 1 over R1 would be 1 over R. I'm going to do 1 over this, so it's going to be sigma 1 pi a squared over L, so L can come on top, plus then it's going to be sigma 2 pi b squared minus a squared here, and that is the resistance. Do you all see this, class? Now, I gave you that formula, and I was looking for that. I'll show you the other way to do it. Actually, there's several, but this is, I'll just tell you the other way. Now suppose this whole surface is metallized, and you put a battery here. You got plus to minus, say, V here, and it goes to this side. Now here's how you would do it if you assume the voltage between the plates. You start with V, then you get E. You realize E would be a constant through here. All the current's flowing this way, right? E would not vary versus the length. It's not flaring outward. It's not like a cylindrical system or a spherical system. E is going to be the same everywhere, okay? So E is just voltage, the actual voltage across the surfaces, or V. Maybe I should call it V naught, so you don't think about this as something that varies. V naught divided by L, and the AZ direction, and you can give this a direction if you want. Call this the Z-axis. Once I have E, then I get J, right? And J is sigma E. So here, I'm going to have J in region, say sigma 1, would be equal to this V, this E field times sigma 1. It would be sigma 1 times V naught over L AZ. And then I would get J and sigma 2 in region 2, which is just sigma 2 times V naught over L AZ. That's the current density in the different regions. The first is in sigma 1, that would be J1, or J sigma 1, and then in this region it's J sigma 2. Agree? Now to get the total current I, we simply would integrate J dot ds over the surface What we're really doing is just taking these values of J, they're scalar, I mean, they're constants, right? There's nothing in here that varies with position, and multiplying them by the surface area. Do you all agree with that? So here, when I take a look at this, I'm gonna take this times the surface area of one, or sigma 1, V naught over L, times the surface area, which is just going to be pi a squared. I can make this a formal integral, but it's no need to do it. Then the total current flowing in the second region would be sigma 2, V naught over L, times pi, and then it would be B squared minus A squared. That would be the cross-sectional area there. Does everybody see this, class? Right. Okay, you all see it? All right, it's important you do. Now, that's I, and then I can get R total is just V over I. The V's are V naught over I. The V's cancel, and you're reduced to the same thing right there. Agreed? When you plug the numbers in, I don't remember this off the top of my head, but what is the value? I actually forgot.
22.74 milliohms.
Yeah, that's right. Times 10 to the minus 3 ohms. You can just stick the numbers in there. How many got that right, by the way? The only thing I could think of was the problem was this area. I don't remember if that was altogether the problem, but I saw a lot of things where it's just, I saw something like this, and then I saw a final answer that was way out, and I didn't know how you got there. So I need to see the steps you take to achieve the final result, because it's got to be clear to me if I'm going to grade this thing fairly. Any questions about this one? All right. Finally. Last problem. Determine the capacitance for a spherical capacitor having inner radius A and outer radius B. This is the one I did on the board. So it has inner radius A, outer radius B, and it's got an epsilon relative here of 3 over R. So what I want is this effective capacitance right here. And it's spherical, correct, class? Now, this is the way I was hoping I'd see it done, because we did this problem for any given dielectric. You assume Q, right? So I'm going to put charge Q on the inner plate, then minus Q on the outer plate. Agreed, class? After that, I get D. So I get D is equal to Q over 4 pi R squared, and it's in the AR direction, and that's in between these regions. Everybody agree with that? Now once I have D, I get E. So I get E equals D over epsilon, or it's equal to Q over 4 pi R squared, and epsilon is 1, but it's going to be 3 over R, that's epsilon relative, right? Times epsilon naught AR. Agreed, everyone, right? And when you do that, I'm going to simplify here. You see that the R squared times 1 over R just lends me an R right there. Right? Now I need the voltage. And to get the voltage, and it's going to be strict positive, I know that, it's the integral from A to B of E dot dl, which is going to be the integral from A to B of Q over 12 pi epsilon naught R AR dot dr AR, that's dl. Agreed? Right? You could put the entire dl on here. You could put, it would be R sine theta d phi, and then R times, what is it, R d theta, A theta, but you don't need to do the others because the A theta and A phi will dot out to 0. So when you do this, AR dot AR is 1, and this will render a natural log. So I have Q over 12 pi epsilon naught, natural log of B over A, and that's V. And finally, C is Q over V. So it's 1 over that, so it's 12 pi epsilon naught over the natural log of B over A. And that's what I was looking for. Follow me on that, class, everybody? Make sure if you're doing these things, if you're talking about a spherically symmetric system with a varying epsilon, you start with assuming Q, get D, get E, get V, then get C. Some people just have that formula memorized, I think. It's 4 pi epsilon naught over 1 over B, 1 over A minus 1 over B. That's only good if epsilon is a constant, right? Not if it's an epsilon relative varies. Are there any other questions here at all? All right, I'm gonna do one more thing. And I'll tell you about any scale on the test. I haven't actually figured that out yet. Now, we're still are in magnetostatics, and today what I'm going to talk about, we talked about magnetic energy. Do you remember that? Magnetic energy density? All right. Well, let me do this. My real goal is to talk about inductance. But before I talk about inductance, I'm going to talk about magnetic energy. So this is magnetic energy. And really, magnetic energy density. All right. In general, energy density, this is electrostatic energy density. Energy density is usually, the symbol is small w sub E, and it's 1/2 d dot E, or it's simply 1/2 magnitude of E squared over, or times epsilon. Now epsilon is epsilon naught times epsilon r. And that's in joules per meter cubed. Do you remember this part, right in class? The electrostatic energy density from chapter B. Does anybody? You do? Okay. Right, remember, it's always proportional to E squared, proportional to epsilon, and times 1/2. So it's proportional to field strength squared. That's energy density. And that's electrostatic. For magnetostatic, energy density the symbol is W sub M, and it's 1/2, and it's really B dot H. And that comes down to 1/2 times mu times the magnitude of H squared, because B is mu H. Follow me? Now those are energy densities, so this is joules per meter cubed. Now, when we want to figure out inductance, this is important, we can do it two ways. One is using the energy density equation, equating it to the bulk parameter energy density. And the second is doing something called flux coupling. Have you had Dr. Gross talk to you about how to calculate inductance using flux coupled through magnetic circuits yet? How many have had Dr. Gross? Oh, you're in for a treat. I'm glad I got you first, but don't say it. I'll prepare you. All right. In general, for for an inductor, the symbol for an inductor is just a coil of wire like that. And usually you see an L there, or if you took circuits, you see something like J 100 ohms, something like that. But L itself is in henries. Well, if I put a current I in there, the total magnetic energy, I don't know if you remember this from Dr. Owen's class or whoever you had for circuits, this is the total magnetic energy is equal to 1/2 L I squared. Does anybody remember that? Anybody? 1/2 Li squared, that's from physics too, that's the magnetic energy in an inductor. So if you've got a current I in an inductor, it's got a value L, that's how much magnetic energy is there. Now the reason that's important, that's how much energy you can get out if you short that current across a resistor. You can dissipate that much energy. Do you follow me on this? And by the way, for a capacitor, if you have a capacitor C and it has a voltage V across it, call it V naught, the actual capacitive energy, this would be electrostatic energy, there is 1/2 C V naught squared. You all remember this one? All right, that's capacitive energy, you gotta know these. And that's magnetic energy. Well, this magnetic energy right here is also equal to the integral of the magnetic energy density that I just gave you over the volume of space where the electric field, or where the magnetic field exists. Do you follow me? Think about that, right? I mean, if there is no magnetic field, you don't have to integrate the energy density over there because it's 0 times anything is still 0. Agreed? So we're going to take a look at this a little more carefully. First, we're going to do the internal energy in a wire, given a given current, and then we'll get the internal inductance associated with that. Follow me? I got just about enough time to do this. So, this is going to be internal inductance. Of wire. So here's how this works. First, draw a wire. Assume it's infinitely long, but we're only going to take a look at a cross section of it. So we have a radius A, and assume first of all current I exists in this wire. And it's uniformly distributed over the cross section. You can say the wire has mu as its permeability. I went over mu with you, right? Mu times, remember that B is equal to mu H, right? Or B is equal to mu 0, mu relative H, right? All right, now listen carefully about this one. So if I assume I is going in there, that has a radius of A, the cross-sectional area is pi A squared. Y'all agree with that? That means I can say from I can get J equals I over area, call that the Z direction, AZ, and that would be I over pi A squared AZ. So that's J, right? Now I'm going to get the total magnetic energy in that wire per meter. I'm going to equate it to 1/2 Li squared and then solve for L. That's my goal. Everybody? So now I come up here and I say in order to get the magnetic energy, I need the magnetic field. So now I take a look at this problem and I say, well, if I have a radius rho right here, I know that the total integral of J dot ds going through there has to be equal to the integral of H dot dl, or the magnetic field that's going to be circulating around there. Do you follow me on this? We've done this problem. This is a long infinite wire. I'm taking a look at a section that automatically breaks down to 2 pi rho h phi. Do you agree? Now what I need is the total amount of current penetrating that, right? Well, I've got J is equal to this, so this here would be a double integral technically. You don't need to do this double integral of J, which is going to be I over pi A squared AZ, right? That's times ds. Well, ds in this case is going to be equal to, I'm going to do it this way, rho d phi d rho, and AZ. So phi goes from 0 to 2 pi, right? And rho will go from 0 to rho. And by the way, that means I technically have to prime this rho, don't I? In there. Y'all see what I'm doing, class? I'm sorry if I'm moving along gotta speed, I'm looking at that clock and I got that call coming. Are you with me? Now, please watch this. So now, what do I really have here? Well, I have I over pi a squared out in front. Now when I come here, az dot az just goes to 1, don't I? Then when I integrate d phi from 0 to 2 pi, I just get 2 pi. And when I integrate rho prime d rho prime, I get rho prime squared over 2 from 0 to rho, or I get rho squared over 2. Are you with me on this? I'm only solving for the h field. So now I can say that my h field, and this is going to be h, or I mean this is going to be this integration, that's equal to 2 pi rho h phi. And I look at what cancellations I can do on this side first, so I can get rid of the 2's, I can get rid of the pi's. And then I have I rho squared over a squared divided by 2 pi rho, or I have h phi here equal to I rho over 2 pi a squared in the a phi direction. That's my h. Agreed, class? Now from there, I have 8:56. Can somebody give me the time? Okay. Well, this is the last part. From there I can get the magnetic energy density. And that's 1/2 mu times magnitude of h squared, which would be the magnetic energy density would be 1/2 mu, and the magnitude of h squared is this square. Must be something I said. So then I have to square this. So I have I over 2 pi a squared times rho squared. Do y'all agree with me? Now I've got to find the total magnetic energy in that section that's 1 meter long, right? So that means the total magnetic energy would be 1/2, well, it would be equal to the integral, triple integral of this, which is going to be 1/2 mu I over 2 pi a squared rho squared, and then the differential unit of volume in cylindrical coordinates is rho d phi d rho dz. And we can throw out the dz integral because it goes from 0 to 1. D phi goes from 0 to 2 pi. And this should be, d rho goes from 0 to a. Do you follow me on this, class? All right, now, when all is said and done, I think you can do this one. I got rho squared times rho is going to be rho cubed d rho. I integrate that, I get rho to the 4th over 4. How about we stop right here, do that integral, and then equate this to 1/2 L I squared, and that would be the internal inductance we can get. We'll pick it up there next time. I'll give you some reading and maybe a few homework problems you can think about. And now I gotta erase this, and I'm sorry, but I have to take